Hello. Random question. Is that backwards for all of you like it is on my screen? Can you even hear me? Am I talking? As I'm talking, can you hear me talking? So many questions. So yes, you can hear me and it's not backwards. Okay. Perfect. Okay, so I'll be here for 5-10 minutes. In that time, then, is there anything specific you would like to review? I'll let you all decide. This is going to be really frustrating, but I'll let you all decide where we go first. What will be on the test? Questions. The whole unit. I don't know what that means. Is tomorrow's test just on packet 4? No, tomorrow's test is on packet 3 and packet 4, so on both rotational dynamics and angular momentum. A little bit of rotational kinetic energy in there, and there's always some rotational kinematics. So stuff like that. Problems like page 6. So Leah, I'm going to need you to be more specific. Like page 6 in the packet number 4. Is that what you are talking about? Yes. Okay. So I'm going to pull up page 6 here. I don't think you can see me pulling up page 6. Maybe you can. That'd be totally creepy. But so questions like, were you dealing with trying to solve? So on page 6, that question dealt with solving conservation of angular momentum for both an extended object, like this wheel, and another object that was traveling into the wheel. Okay, so with this situation, this doesn't even look like it's going to hit the wheel because I drew it too low. Oh, look at that, it hits perfectly. But I have this situation where I have an object traveling in a straight line, and I have a disk which is not moving. So let's just pretend like this is my situation. I have an object of mass m. A disk has a moment of inertia of 1/2 mr squared. So we can say that this disk has a radius r, has a mass m. And as this travels, then it has an angular momentum about this axis that I have here, right? So my angular momentum is about my axis. So then my question is, if I'm trying to solve for angular momentum of a point about an external axis, then my angular momentum is given as mvr sine theta, where my theta is the angle between my r and, in this case, this would be my v. So that's my theta. Now, the interesting part about question like this is that this second piece, this r sine theta, is this side. And as my object moves into the collision, that side stays constant. That r sine theta side stays constant. So it never changes. It doesn't matter what r is. It doesn't matter what theta is, because even as it travels, r will decrease, but theta will increase, and they'll cancel out. And I'll get this side r sine theta. On page 6, I believe that's called b, is that side. And that's always true. So if you know that distance from your axis vertically down to where your point hits, whatever that distance is, then you can figure out what your angular momentum of your point is, because that stays constant. So in this case, like on that problem on page 6, it's mvb. That's my side length there. So I would know what my angular momentum is there. After they collide then, that's still my angular momentum. But now when they collide, there's a torque between them. And now I have a situation where this object does rotate because of that torque. So when I have my new I have to take into account that now I have not only the disk, but also that mass away from my axis of rotation as well. Hi, Ellie. Okay. So then as I'm going and solving this, now I have a new I, but my angular momentum at the end is still the same as it was at the beginning. So say, for example, I wanted to know what this angular speed was, then I know based on my angular momentum equation that it would be L over I, and I could solve knowing both L and I. Does that answer your question, Leah? Or should I somehow keep going? It's mr squared because anytime you have an object whose axis is external to it, then that's when you do the sum of mr squared to solve for what the moment of inertia is. Okay. If you have an object that's rotating within itself, that's when you get the things like the 2/5 mr squared, the 1/2 mr squared, the mr squared for a hoop, the 2/3 mr squared for a hollow sphere, things like that. Okay. So Leah, I hope that answered your question. If it didn't, please let me know and I will go back to it. But for now, I'm moving on to, will impulse be on the test? Yes, impulse will be on the test. But we're talking about an angular impulse. And when you're talking about an angular impulse, okay, good. When you're talking about an angular impulse, you're talking about how a change in angular momentum occurs would be an angular impulse. And in order to change an angular momentum of an object, you have to apply some net torque for some period of time. Very similarly to how if you change a linear momentum, you have to apply some net force for some period of time. But we're looking at rotational pieces, so we need to look at rotational pieces. That is how we go about doing that. Is mr squared. I talked about that. Whenever an object rotates, does it have torque? Whenever an object has an angular acceleration, it has torque. Okay, because remember, in order to cause an angular acceleration, I need some torque applied over some period of time. Very similarly, if I want to have a linear acceleration, I need some net force applied, okay, in order to make that happen. If this is on the test, but could you do an example with multiple steps, like multiple equations? Cheryl, you're going to have to find me one. And if you find me one, I would be happy to go through and do that. Can you explain the parallel axis theorem? Sure. So the parallel axis theorem is just a way to go through and determine the moment of inertia of an object when its axis is different than expected. So let me just give you the easiest one to talk about. If I have a long, thin rod, its moment of inertia about its center of mass, we know. I like my axes to be hearts. Its moment of inertia about its center of mass is 1/12 ml squared, where m is the mass of the rod, L is the length of the rod. Okay, let's say, for example, though, that I have a situation where it's not in the middle. Let's say I move the axis to the end. Okay, so instead of being in the center, I'm going to move it to the end because I can. So I'm going to move it to this end. And the question becomes, what is my new moment of inertia when I do something like that? Well, I take, this is my moment of inertia, is my original moment of inertia plus, and you can write this as L or D or whatever it may be, but it's the mass of the object times the distance the axis moved. So in this case, I moved my axis from here to here, so I moved it L over 2. So as I write this then, I'm going to say, okay, well, originally at this point, it's 1/12 ml squared, but then I moved it L over 2 squared. Okay, so then as you go through, I can solve this question and say that's 1/4 ml squared. So then This is 3/12 ml squared, and then in the end, I get 1/3 ml squared, which is another one that we do know. The moment of inertia around the outside or on the end of a long, thin rod is 1/3 ml squared. Okay. Aisha, I hope that makes sense. Can I repeat what, Christine? Okay, so as we're going through the parallel axis theorem, keep that in mind, right? What is my original moment of inertia about some point that I know, and how far does it move? Okay, excellent. How is the test going to be laid out? Oh, hold on. I got another question up here. Page 11, number 1. Okay. So let me get page 11, number 1, because I don't know what that is. So another thing is remember that the answer keys for all of the problems in the packet have been posted on Google Classroom. I'm happy to go through this problem with you, but just as an FYI. Okay, so as I'm looking at page 11, number 1, I have a disk. Okay, and this disk is rotating at 7 revolutions per second. Oh, you can't see that. Just move that up a little bit. Okay. A non-rotating rod of the same mass and length as the disk is dropped onto it, and then they spin together. What is the angular velocity? So the first thing I know in this situation, it has a mass m and it's rotating, and if it's a disk, its moment of inertia is 1/2 mr squared. Okay. Then I have a situation where this disk gets something dropped onto it, and that something that's dropped onto it has the same mass, has the same diameter as the disk, and rotates about the same axis, which is through the center of mass. So in the beginning, I have just the disk, and at the end, I have this disk and rod both rotating. Well, my moment of inertia then of the disk stays the same. It's still 1/2 mr squared. The moment of inertia of this second thing, this rod, we just talked about this, rotating about its center of mass, is 1/12 m. Now my L in this case is 2 times my radius squared. Okay, so now I'm going to have a new moment of inertia associated here, and I can solve for what that new moment of inertia is by adding these two things together. 1/2 mr squared plus, let's see, that's 4, so 4/12, 1/3 mr squared, or 3, 5, 6 mr squared is my new moment of inertia compared to what it was before at 1/2 mr squared. Anytime I have a collision, then I know that my initial angular momentum is going to equal to my final angular momentum as long as we're rotating about the same axis. So in this first situation, I have 1/2 mr squared times omega naught, remembering that this is I omega, equals 5, 6 mr squared times omega. And from there, I could continue solving this question, knowing that m is going to cancel and doesn't matter. R squared is going to cancel and doesn't matter. So I get 6/10 omega naught equals omega. Well, omega naught is 7. So from there, I can solve for what my answer is. And at that point, it's a calculator-based problem. Okay. Okay, how is the test going to be laid out? The test is going to be on Mastering Physics. There are, let me see if I can remember correctly. You will get 12 multiple choice drawn from a bank of Mastering Physics for some reason. I suggest you scroll all the way back to when we signed up in September if you're one of my students, if you're one of Ms. Ross' students, and all the way back to January if you're one of Mr. Corman's students, and make sure that you get an account. And it will be, as Ms. Roth said, the test will be open from noon to 5. You have an hour to take the test. You have to start it by 4, otherwise you will run out of time. And finding angular momentum, what clues us in on whether we use MVR sine theta or I omega? If the object has an internal axis, so it's rotating about itself, then use I omega. If the object is moving towards something else and its axis is outside of it, use MVR sine theta. That's the best way to remember that. If my object is rotating inside of itself, so like this, right? If it's rotating about itself, that's my I omega. If it's rotating about some external axis, that's my MVR sine theta. Is there anything we should focus on more than something else? Like, are there more impulse and torque question or rotational? There's not very many rotational kinematics questions. Those would all just be based on the situation where you were trying to find an angular acceleration. Just remembering your equations associated with rotational kinematics. I'm not sure it's worth studying it super to its extent. Just make sure you remember how to use your kinematics equations, and you should be okay. And remember that anytime you have a situation where there's a torque applied, you can figure out, as long as it's a constant torque, you can figure out what your angular acceleration is if you know your moment of inertia and work that way or work backwards. Just keep that in mind. It's on Mastering Physics. Yes. There are some multiple choice and some free response. It is not on Mastering Manager. It is on Mastering Physics. I think Mr. Corman messed that up. Yes, work will need to be shown. So with your free response questions then, tomorrow at noon, an assignment on Google Classroom will go up, and it will be necessary for you to take a picture of your work and submit it. So before your test can be graded and completed, you will need to take a picture, just like we're doing here, right? You'll need to take a picture, tell me your question, just what the name of the question is, and then show your work. And that will allow one of the teachers to go through and grade based on that. How many questions are there? Can you go through number 7? Number 7 on the torque quiz. I don't know what number 7 on the torque quiz is. I'm going to need to look at the torque quiz. Now, if I was Mithra, where would I put the torque quiz? There it is. Number 7. Oh, sure, I can go through this question. So number 7 on the torque quiz, I have a pulley, and then there's a mass hanging from the pulley, and it asks me what my graph is going to look like. If I look at the axes associated with my graph, the object or the situation tells me that it starts at rest, and then the block is dropped, and as the block drops, it accelerates. But on my axes, it gives me torque, and over here, it gives me final angular velocity over time, which we know is acceleration. So it's my angular acceleration versus torque graph. And the question is, which one of these is it? Well, I have a number of options, right? I know, first of all, that my object is going to be speeding up. So I know that I can't have a graph that looks like this, because this is telling me that my acceleration rate is decreasing. So it can't be that. Okay? I cannot have a situation like that. My angular velocity over my time is not working like that. Okay? So as I continue to look then, oops, I forgot what the other graphs look like. One moment. Okay? As I continue to look, I'm looking at how much torque I have to apply in order to make it happen. This is saying that as I apply more torque, my angular acceleration rate is decreasing, which doesn't make any sense. Okay? Now, what is it that has to happen? Well, I have essentially 3 options here based on what's going on. Let's talk about all 3. I have a blue option, I have the red option, and I have the orange option. And each one of these is saying a different thing, okay? The blue option is saying that as soon as I apply a torque, I'm going to have an angular acceleration. That's true as long as there's no resistance associated with my pulley. As long as I have no friction or resistance associated with my pulley, then I will get a graph that looks like that, okay? My orange graph is saying that even if my torque is 0, my object is going to have an angular acceleration. It's going to rotate even if nothing is pulling on it. It's going to rotate and increase its rotational rate even if nothing is pulling on it. My red graph is saying that in order to even start its rotation, I need to apply a minimum amount of torque to overcome some sort of frictional force acting on my pulley. Then I can accelerate. So, given in the problem, it tells me that there is considerable friction in the pulley. So with that being said, then, I would need some torque to be applied in order for this to happen. Okay, so then my red is my answer. Can you go over what happens with the gravitational force when the pivot isn't on the center of gravity or one of the ends? Like that free response on the quiz. So can I go over that question on the quiz? Like, I don't understand what that means. Can I go over when the gravitational force? Whoa, lots of things. I'm like way back here. So I'm unsure what you mean, but I'll try and explain based on what I know. So like the one on the quiz is a rod, but its axis is here. Anytime you have a massed object, and that's the key, anytime you have an object with mass, and it's not balanced about its center of mass. So let me say this. Anytime you have an object with mass, and it's balanced about its center of mass, you're going to get this torque on the left, torque on the right, caused by the gravitational force. But since those distances are the same, and the amount of mass on each side is the same, and they're opposing torques, we can almost not even think about them because they don't really matter if we're trying to solve a problem. So we don't even write them down because they aren't even a situation where we need to pay attention to them. They immediately cancel each other out. When you move your axis so it's not at the center of mass, now I have a situation where I have a smaller amount of mass on one side and a larger amount of mass on the other side. And I have to take into account that one of these torques is larger than the other, because now I'm going to get a net torque acting on my object. Also, these R values are not the same because I'm in the center of this side of my mass. I'm in the center of this side of my mass. And since this one's shorter, it's not as much as this one. Okay, so can you go over what happens? Yeah, so I think that goes over what you were asking, Ali. And if not, I'm sure I'll see down here as I scroll down. I think we're going to submit pictures of work on Google Classroom. You are. Do we need to have all the inertia equations memorized? You don't need to have any of them memorized. Number 6 on the torque quiz, the answer would be E0 because the center of mass is not moving. Thank you, Cheryl. Does the angular momentum always stay constant from the beginning and the end as long as there is not an external net torque? Or if the axis does not move? Can you repeat how the test will be laid out? Sure. You get, what did I say? You get 12 multiple choice questions randomly drawn out of 25. Mastering Physics will do that for me. You get 2 free response questions, randomly drawn out of 5. Again, Mastering Physics will do that for me. Write the name of your question as you're doing your work. Write the name of your question on the top of your page. Do your work. Submit your answers on Mastering Physics, but then you'll also have to submit a paper with your answers in your work to Google Classroom. It froze. I'm sorry it lagged. Why is 3 on torque quiz C and not D? Actually, Cheryl, I answered that question on Flipgrid today. I forgot who asked that, but I just answered it. So I'm going to leave that up to Flipgrid. Check that out. Will there be free response questions? Yes. Is it on Mastering Physics? Yes. 12 plus 2, 13 plus 2? Yeah, about 15, something like that. Cheryl, the answer for D is 60. But okay, 12 multiple choice. I don't know what he said after that. Angle is between R and the other thing. It says that the angle is 30. Can you go over number 2 from the quiz? Not sure why I'm stuck. Thank you. Number 2. I think I still need to do number 2 on the quiz. Number 2. Yeah, number 2. I can do number 2. So I have a multi-step pulley. I have multiple forces. This is 2F. This is 3R. This is 2R. This is F. 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 I'm just copying down this picture to make sure that I got them all. And I did. I got them all. So here I have this. Now, what I'm looking for when I'm looking for a net torque is I'm looking for which of my forces are going to cause a clockwise torque, which of my forces are going to cause a counterclockwise torque. So in this case, I have 3 forces that will cause a counterclockwise torque. 1, 2, 3. And I have 1 force that will cause a clockwise torque, 1. So that's going to be my subtraction. Now remember, torque is RF sine theta. Since this is a circle, all of these forces are tangent to the circular path. So I don't have to worry about this because it's going to be sine 90 each time, which we all know is 1 at this point, right? So I'm just looking at RF, and I'm going to go counterclockwise first, then clockwise. So let's start with this first one. It's all the way out here. 3R is my R value. F is my F value, sine 90. Plus, still in the same direction, 3R is my R value. F is my force, sine 90, plus 2R is my R value. F is my force, sine 90. Those are all in the same direction. Minus this one. I'm going to come down here. 3R is my R value. 2F is my F value. And that will all equal, those are my only forces. All of those together will equal my net torque. Well, as I go through and solve this, then I get 3 plus 3 is 6, plus 2 is 8. So I get 8RF minus 3 times 2 is 6RF, which gives me a net torque of 2RF. Is the angle, okay. Mr. Metzler explains on Flipgrid. Oh, okay. Will we be on one question until we finish answering it? You will be on one question until you finish answering it. Yes. You cannot skip around. Will the work have to be on paper? It'll have to be on something that you can take a picture of and submit. So it could be paper. If you have a whiteboard or a chalkboard, I don't know, something where I can see your work is what I'm looking for. Let's see, where was I at? Is there a time limit? 1 hour is the time limit. The second free response question on the torque quiz. Wasn't there one free response question on the torque quiz? Serious question. Like part B or part C? Isha. Now I'm going to scroll down to see Isha. You can put your work on your iPad as long as then you can take a picture of it and send it. That's fine. Okay, so I'm waiting for Isha. Just write the name of the free response question. Yeah, each one has a name. Just write what it is. The flip code is currently on Google Classroom. There are 2 forces because now the gravitational force does occur at the center of mass, but when you place an axle at a point, then you have essentially 2 separate masses providing counter torques on one another. There are both conceptual and computational. The answers for the quiz are not going to be posted with work and explanation, Harry. That's why we're here now. Isha, part C and D on the quiz. Okay, so I'm going to look at the torque quiz again. And then I'm going to go back to Julia's question there. Okay, so part C and D and part B. So I'm just going to go over the question. So let me get a new sheet of paper here and then look at the question again. So let's see. So I have my beam. And the first question is, what does the free body diagram look like? The second question is, use the parallel axis theorem. The third question is, I have masses. Okay, so I'll go back to that when I get to it. So here we go. So this first question, I have an axis here. And if my axis is moved, then I'm going to have a force from each mass on each side at the center point. So I'm going to call this my gravitational force left. At this center point, I'm going to call this my gravitational force right. This is going to provide a larger torque because it has a larger mass associated with it. I have a tension force from this string applied here. Then I have my pivot applying a force. My pivot has to hold my object up, so I'm going to say this is the force of my pivot vertical. And since I have a leftward horizontal force, I also need a rightward horizontal force in order for this to be at equilibrium. So I get something that looks like that. So then my next question is, using my parallel axis theorem, show that my new moment of inertia is something else. Well, we talked about moment of inertia in parallel axis theorem just a little bit ago. Okay, so I'll choose the center because I know what the moment of inertia about the center of mass is. It's 1/12 ml squared. And then the question is, how far did I move my axis? This is my D. How far did I move my axis? Well, I believe this left side is L over 4. So then this is in the middle. So then this D value also has to be L over 4. So the mass of the object times L over 4 squared. So then as I go through, I get 1/12 ml squared plus 1/16 ml squared. And as I add my fractions, I need a common denominator. And then I can add my numerators. So I get 7/48 m squared. Okay. Okay. Question C says that now all of a sudden I have these additional masses. So now if I have additional masses, I have additional forces, and I need to take those additional forces into account in my situation. So I'm going to have my same forces that I had before. My gravitational force left, my gravitational force right, my tension force, my pivot horizontal, and my pivot vertical. And then also in this case, I'm adding two forces. I'm adding this force on the right, we'll call 3mg, the weight force from this 3m mass. And this force on the left, we'll call 2mg, this weight force from that 2m mass, whatever it may be. So the question is, what is the net torque about the axis? Well, then I need to figure out, okay, which ones of these things are providing a counterclockwise torque, which ones are providing a clockwise torque, and go from there. Well, RF sine theta is my torque. So I'm going to keep that into account as I go through and try and determine my net torque here. So let's start all the way on the left. This is a counterclockwise torque. Its distance from my axis to the force point is L over 4. The force itself is 2mg, sine of 90 degrees. Those are at 90 degrees to one another. Okay. This force from gravitation on my left side Well, this whole thing is L over 4, so then halfway in between that is L over 8 from my axis of rotation. This is part of my mass. The whole mass of the beam is m. This is a quarter of that beam, so then it's a quarter of the mass. So then a quarter of the mass times g is my gravitational force times sine 90 degrees. That's the second one. The third force is the force from my pivot, but it's 0 from my axis. Its distance from my axis is 0, so it will not provide a torque. The force from my pivot horizontal, again, 0 from my axis, so it will not provide a torque. I don't have to worry about it. Let's keep going. The force gravitation on the right. Well, this whole beam is 3/4 L, or 3/4 of the length, so this is in the middle of that. So that's 3 over 8L is my R. My force, well, if this is a quarter of the mass, then this is 3/4 of the mass. So 3m over 4 times g times sine 90. That again is 90 degrees. Okay, let's keep going. I'm running out of room here. This 3mg force, its distance from my axis to the point of force application is 3 over 4L times the force, 3mg, times sine 90. Okay. Last force, I have my tension force, which again is a distance of 3L over 4 from my axis of rotation to my point of force application times my tension force times sine of, and I believe it tells me this angle is theta. And since this is in rotational equilibrium, everything together is going to equal 0. So now it's a question of which ones are counterclockwise, which ones are clockwise, and how do they cancel each other out. This one's counterclockwise. This one's counterclockwise, so they're going to add. This one is clockwise, so I'm going to subtract. This one is clockwise, so I'm going to subtract. This one is counterclockwise, so I'm going to add, and all of those together equals 0. That's how we set that up. Then from there, it's a situation where we just have to go through and solve, what does this all mean in the end? So this first one, I get mgl over 2 plus, what's this? mgl over 32, gross, minus 9mgl over 32 minus 9mgl over 4 plus 3L over 4 times Ft sine theta. Okay. So I guess we have to find a common denominator. Do I have to keep doing this, or can you go from here? I guess I do, because I need to solve the next part. Okay, so 16 mgl over 32 plus mgl over 32 minus 9 mgl over 32 minus, let's see, that has to be times 8. So 72 mgl over 32 plus 3L over 4 Ft sine theta equals 0. 17, 8, man, 8 minus 72, 66, no, 64, my apologies, 64 over 32, so that's 2. So negative 2 mgl plus 3L over 4 times Ft sine theta equals 0. Okay. So I think I'm going to get this right before the end. So I'm going to add that over. I'm going to multiply by 4. I'm going to divide by 3. Notice my L cancels out. So I get 8/3 mg divided by sine theta equals Ft. Wow, that was fun. Okay. So then for the next question, it says the cord is cut. Okay. What is the angular acceleration? Well, the nice part about this question now is that now I've figured out, well, if there was no tension force, all of the other forces then gave me a torque of -2 mgl. And I know that my angular acceleration is net torque over moment of inertia. And in one of the previous problems, I already solved for what that was. So I get -2 mgl over 7/48 ml squared. M cancels, one of my L's cancels, 7/48. I guess if it's net, or it doesn't really matter what this is, as long as it's magnitude. The negative sign doesn't matter. So 48 is 96g over 7L is my angular acceleration. Okay. That's how you do part D. There's a lot of things here. Okay, let's see. Will we get graded right away? The multiple choice is graded right away, but you won't be able to see your score. You do need to show work for short answer. Number 10 on the quiz. I'm assuming you mean the torque quiz, Harry. So that's where I'm going. I need a new color. These are all boring. This is fun. There are 43 of you here. That's crazy. So how are you all doing? I hope you're all doing well. So number 10 on your torque quiz, you have an object like this. It's rotating. Its axis is here. Okay, and the gravitational torque on this object is from its center of mass, so it's right here is my force application. Okay, this distance then is L over 2. Okay, and it says that my angle from my vertical is 30 degrees, which means that as I draw my R and I draw my F, my angle is 30 degrees between them. So my net torque is going to be L over 2 is my R, mg is my force, sine 30 degrees, which is a half. So I get mgl over 4. Now, since this is a rod rotated about its end, it tells me in the problem that's 1/3 ml squared. So my angular acceleration as net torque over moment of inertia is mgl over 4 divided by ml squared over 3, which if I divide by a fraction, I can multiply by the reciprocal. So that's what I'm going to do. Notice that my m cancels, one of my l's cancels, and I get 3g over 4l. That's my answer to number 10 on the multiple choice part of the quiz. Are there worked out answers for the rest of the angular momentum packet? Yes, there are. They should be on Google Classroom somewhere. I think in classwork. What problem are we looking at? Free response on the quiz. Yes, free response too. So when you change the axis of rotation, there will be 2 gravitational forces on the object. Yes, Anthony. How can there be 2 forces of gravity? So anytime you have a situation where you have varied masses, so there's always gravitational force on each side. Anytime you have a mass, you're going to have a gravitational force on each side. And I explained this earlier, I think. But the only difference with this is when we talk about this object, if we were looking at how this object was behaving, then this is how it keeps from rotating. This is why it's balanced, okay? Because the amount of mass on this side at its center is the same as the amount of mass on this side at its center. So those torques cancel one another. It becomes an issue when that axis moves because now I don't have equal gravitational forces on each side, so I have a gravitational force from each, right? I can almost think about it like 2 separate objects rotating, okay? And I want them to cancel. Those are on different sides of the axis. If it doesn't specifically say use the parallel axis theorem, you would only have to do it if you were trying to figure out what the moment of inertia was, and it wasn't given to you. By mass. So the mass of the board is M. Okay, so now I'm going back because now I'm like reading questions as I'm going through what was happening. So the mass of this whole board is M, and this is a quarter of the board. So if that's a quarter of the board and it's a uniformly distributed mass, then that's a quarter of the mass. The theorem is necessary when the pivot point is not a traditional location used in the moment of inertia formula. That is true, Leah. Whichever side the center of mass. That is also true, Joseph. Whichever side the center of mass of the whole object is on is the side that will fall. And the way that we can analyze it is by breaking up the mass either way. You can do the problem without that assumption and still get 8 mg over 3 sine theta. Cool? Neat. Ooh, good point. The moment of inertia does change. I guess I should have fixed it based on those masses added. Oh, well. That's another problem for another day. Number 5 on the torque quiz. Number 5 on the torque quiz. I think this is one. No, maybe I didn't. So number 5 on the torque quiz. I have 3 masses, M, M, and M. Okay. And they're spread out. This is L over 2 distance, and then another L over 2. Yep. So then this total distance is L. And when I'm doing my moment of inertia about an external axis, this one is about its axis, but the axis is external to it. So then its distance from that axis point is 0. So I get my moment of inertia is the sum of mr squared, which is m times 0 squared plus m times L over 2 squared plus m times L squared. And as I do that, I get something that looks like this. And I can solve for my moment of inertia then. I'm glad you're doing well, Ellie. What is Anthony's valid question? Oh, does the moment of inertia change? Yes, Anthony is correct. The moment of inertia does change. It is no longer 7/48. It would be 7/48 ml squared plus, let's see, what is that mass? 2m times L over 4 squared plus 3m times 3L over 4 squared, whatever that is. Okay. And then that will give me my new moment of inertia, 9 over 16 that can be used to solve this way. Okay, my net torque stays the same, but my I is different. Remembering that I should have added the masses in when I went through and did the problem. Number 9 on the torque quiz is also one that I did on Flipgrid earlier. So that's there for you as well. So you can go check that out, Valentina. Is it time to go? Are you all done? That's all you have? I guess not. What does this end up being? $87, $94. Number 2, page 11. Is this page 11 in the packet, Julia? Packet number 4? Yes, okay. Okay. So what is this question? An asteroid of that large mass traveling at a speed of that much hits the Earth at the equator, hits the Earth tangential. So there's a lot of things I need to know before I can actually solve this problem. And question 1, page 11. I just did question 1 on page 11. So first thing, my asteroid is traveling inward, okay? And it's going to hit at the equator. So that tells me some information that I need to know. I know that the Earth is already rotating in the direction of the Earth's rotation. Perfect. So it's going this way. The Earth is already rotating. The Earth has a mass. The Earth has a radius, right? These are all pieces that we know. So let me write this stuff down. That way I can remember it, and then we can go from there. So 100,000 kilograms. It hits going 30 kilometers per second relative to the Earth, hits the Earth at the equator. Okay, find the fractional change in angular speed. Okay. Hi, Maha. How are you? So as we look at this problem, then, I have a situation where I have an object traveling into one situation. Both of these objects have angular momentum at this point, right? So then how do I go about solving this question? Well, first off is I need to know the mass of the Earth. I need to know the radius of the Earth. I believe this is 5.98 times 10 to the 24th kilograms, I think. I believe this is 6.38 times 10 to the 6th meters, and I hope somebody checks me on that. Is everybody checking right now? Because I guessed. Okay. So as we look then, we'll assume those are right, or we can just leave it as variables and go from there. When I have a situation like this, my angular momentum is going to be 2. I have mvr sine theta, we'll talk about that in a minute, plus I have the angular momentum of the Earth, I omega. All of those things are things I'm going to need to know as I move forward. At the end of this situation, I have this sort of situation. Okay? And the question is, how much has my angular speed changed, or what fraction is it different than it was now? So what I do is I would look at a ratio, because I know L equals L, their angular momentums are the same. So mvr sine theta plus I omega equals I plus mr squared omega. Okay, so if I look at a ratio of these two things, let's see, I have to subtract that. Blah, blah, blah. Oops. I'm like blanking on math today. What am I trying to do here? That would be my new answer. Okay. Now, this information I all know, right? These are all numbers at this point. So I can figure out what my new angular speed is compared to my original angular speed, knowing that this is 2 pi radians every 24 hours, right? And then I can go through and I can solve. If you were given a question like this, you would have to be given that information because I don't even remember it. And it may be on your equation sheet, but truthfully, I don't know the answer to that. Does J equal change in P equals F, change in T equals M, change in V, transfer over to rotational momentum? Yes, but there is no letter J. There is a change in L, which equals a net torque times time, which equals I, and this is where it gets complicated because it could be delta I or it could be delta omega. Either one of those things occurs. So you need to know which one. But yes, that does transfer over. Objects with mass distributed farther from the axis of rotation have a higher moment of inertia. That is correct. A higher moment of inertia for the same torque does give you a smaller speed. Does the pulley need to have mass as well? If the pulley doesn't have mass, then it doesn't have a moment of inertia. And if it doesn't have a moment of inertia, then you don't have to worry about how it's resisting motion. That's when the pulley comes into play, when it has mass. Generally, there's friction on the pulley to keep the string on the pulley and to keep the string rotating the pulley. Otherwise, there's generally no friction between the axle and the pulley, which I don't know if that's what Anthony's asking. Duration will be 0, make it undefined. Where did I plus mr squared omega? So when the asteroid hits the Earth, right? And let's look at like top view, like I'm at the top of the Earth now. When the asteroid hits the Earth and it hits at the equator, now all of a sudden I have an object on the end, right? At the distance r from the center of the Earth. And I have to take into account that mass, knowing that my object still, my Earth, is still 2/5 mr squared, right? About its own axis of rotation. And then I'm going to keep rotating like that. Would you add those inertias in an inelastic collision? Yes. Add the inertias in an inelastic collision. Blah, blah, blah. Hi, Izzy. Number 5 on page 13 of the 4th packet. To find the final angular velocity, do we have to set L not equal to L final? I'm unsure what that means. So I'm going to have to look at that question to know what that means. Number 5 on page 13. A bullet of mass 5 grams. Okay. To find the final angular velocity, do we have to set L not, oh, like L naught? I got you. I got you. Like this. L naught equal to L final. Yes, that is exactly what you need to do in order to solve that problem. Do you still wish for me to go over it? Wait, Valentina's going to go over it. This is the best. Valentina should YouTube live. Can you see comments on YouTube live? Like if I like post this, will the comments still come up? Serious question. Maybe not. Neat. That's all for the bullet. Just like that. Right? So M is the mass of the bullet, V is the velocity of the bullet, R is the distance from the axis, which is the radius. I is a disk, right? So 1/2 mr squared plus mass of the bullet. I guess I should make this a different M. Mass of the bullet, radius, it hits on the edge, right? Times omega, just like that. How long is this stream going to be? Until you all stop asking questions. It looks like you're all winding down. I might have to go. So I comes from the object that got hit. Correct. My tea is cold. No, not always, but it will always be the sum of the moments of inertia, Christine. It will always be the sum of your moments of inertia when you have an inelastic collision like that. So the moment of inertia of the bullet in this case is about an external axis from itself, so is mr squared. Cold tea is better than no tea. That is true. Aren't you all excited for the test tomorrow? I know I am. No. If you keep asking questions until tomorrow, I will stop at 8:30. If it's an elastic collision, then you just keep them separate. So, like, let's say the bullet hits and it bounces, right? Then you just keep them separate. I have one object moving at one speed at the end, and I have another object moving at another speed if it was rotating at the end as well, or perhaps then it moves linearly again. So that's like the situation where you had, what did we do? We did the block and the marble, right? And the marble went in and then the marble went out. With that situation, I had MVR sine theta at the beginning, right? Where here was my R, here was my V, here's my theta. So that's my R sine theta side. That's constant. And then at the end, this thinger block was rotating. So it had I omega rotating about an axis internal to itself. And this went backward, right? So then I had MVR sine theta also at the end. Now, these rotations were also in opposite directions. So one of them is negative. I don't know where I left off because then I started talking. Just like that is what you would do if it was an elastic collision. Why are you terrified? Hey, Mr. Metzler. Hi, Aqua. How come when calculating the angular momentum of an object, the units are, I don't know what that said, kilogram meter squared per second and not kilogram meter squared times radians per second? Because radians is not a unit. Angular momentum still is conserved in an inelastic collision. Yes. As long as the rotational point doesn't change. I like how you're all arguing with Iqua about what radians are. That's pretty funny. Packet 2, page 13. I don't know what that means. Like the whole page? Oh, wait, we just did this one. With the bullet. That's what we were just talking about, Alexis. That's fun. In a perfectly inelastic collision, yes. Units cancel out. You're all doing great. You're all doing great. Did you know that you can answer each other's questions on Flipgrid too? I think Lisa did that earlier. She answered one of the questions. It was awesome. I was like, I should give extra credit for this. I considered it. I hope you're all doing well. I hope you're all healthy, well fed. The red diagram you drew is still part of the bullet. Yep. Thanks, Asher. Okay, 3 minutes. My purple marker is still open. I'm excited for this test tomorrow. I think it's going to go really well. I'm glad you're eating, Joseph. That's good to hear. I'm glad it was a great review. Izzy, I don't know what you're talking about. I hope you all have a wonderful night. Keep putting questions on Flipgrid. Myself or Miss Roth or Mr. Corman or Lisa will be answering questions on that through tomorrow, through the test time. Remember, your test time starts at noon. You have until essentially 4 o'clock to start because it closes at 5. Don't forget. Okay. I will end the stream. I will post the stream. I will put it on Google Classroom. I hope you all have a wonderful night and good luck on your test tomorrow.